Hello everyone. Today we are going to learn about deadlock avoidance. The learning outcome of this session are: at the end of this session, student will be able to elaborate deadlock avoidance mechanism and identify the safe sequence of process execution. Just recall that deadlock prevention which we studied in previous video. So, we require 4 necessary conditions for deadlock to occur. That 4 necessary conditions are mutual exclusion, hold and wait, no preemption and circular wait. If all these 4 conditions are present in the system, then deadlock definitely occurs. And if deadlock occurs, then it results in low device utilization and it gives reduced system throughput. So, if deadlock prevention mechanism is not present in the system, then we must design deadlock avoidance. Deadlock avoidance means we have to avoid deadlock which try to enter into the system. So, what deadlock avoidance is? Deadlock avoidance requires additional information about how resources are to be requested. For example, suppose we have two processes, process P and Q, and we have two resources, tape drive and printer. Suppose the first request made by process P is to tape drive and then second to printer. Then process Q, first request is printer and second request is tape drive. This is already known to the system that which request is made first and second by which process. If this is known, then system can decide for each request. And to avoid possible deadlock, each request requires that in making this decision, the system must consider the resources currently available. How many resources are currently available? The resources currently allocated to each process, how many resources are currently allocated to each process, and the future request and release of each resource. Means whenever there are number of processes and if system already know that which process will request which resource and which in which sequence, then system automatically can decide whether to allocate that resource to the process or not. And this decision is taken based on these 3 conditions, that is how many number of resources are currently available, which resources are currently allocated to each process, and what is the future request or release by each process. So, each process must declare the maximum number of resources of each type that it may need. Then we have to construct an algorithm which will ensure the system will never enter a deadlock state. Means if system already know how many maximum resources are needed by the process, then it is necessary to design an algorithm which will state that deadlock will never occur in the system. So, that algorithm is called as a deadlock avoidance algorithm. This algorithm dynamically examines the resource allocation state. So, to ensure that the circular wait condition can never exist. So, it dynamically examines the resource allocation state to ensure circular wait condition can never exist in the system. So, the resource allocation state is defined by number of available and allocated resources and the maximum need or maximum demand of each process. Just think that for avoiding a deadlock in a system, what is prerequisite for operating system? Pause the video and think and write down your answer. Okay. So, to avoid deadlock to occur in the system, it requires additional information about how many resources are requested by that process in near future and how many resources are allocated to that process. Now, the first algorithm which we are going to study is a safe state. So, a safe state is a state, okay, we can say that a state is a safe if the system can allocate resources to each process up to its maximum need, okay, in some order and still avoid a deadlock. So here we can say that a system is in safe state if it allocates all requested resources to the process and still it is avoiding a deadlock. That state is called as a safe state. So a system is in safe state only if there exists a safe sequence. What is safe sequence? A sequence of process, for example P1 to Pn, is a safe sequence for the current allocation state if for each process Pi, the resource request that Pi can still make can be satisfied by the currently available resources plus the resources held by all the Pj with j is less than I. Means what? Suppose we have n number of processes, set of n processes P1 to Pn, then we can say that all these processes are executing in safe sequence, means P1, then P2, then P3, then P4, like that. They are executing in safe sequence if and only if system is able to satisfy the request made by process P2, okay, along with already P1 has already its own resources, means some resources are held by process P1 and still process P2 can also satisfy its resource request. Then we can say that P1 and P2 are in safe sequence. Similarly for P3, P1 and P2 already held some resources and still P3 can get the resource from the system, means it is in safe sequence. So if the resources that Pi needs are not immediately available, then Pi must wait until all Pj have finished, and Pj is nothing but j is always less than I. Means if P2 needs to wait, that means it is waiting for the resources held by P1. So if P1, when P1 release resource, then only P2 will get that resource. Okay, then it will be in safe sequence. When they have finished, then Pi can obtain all its needed resources, completes its designated task and return its allocated resources and then terminate. So all process Pi will get its all needed resources, it will execute and then process will terminate, and while terminating it will release all the allocated resources so that other process can use it. When Pi terminates, the Pi plus 1 can obtain its needed resources. Means when P1 terminates, P2 will get resource. When P2 terminates, P3 will get resource, and so on. So if no such sequence exists, then the system state is said to be unsafe. So as shown here, we have a safe state and unsafe state. As we can see here, unsafe state is always a deadlock state. Okay, but safe state is not a deadlock state. Conversely, a deadlock state is an unsafe state. So not all unsafe states are deadlock state. This is again a statement that not all unsafe states are deadlock states. Some of the states in unsafe are deadlock states. All unsafe states may lead to deadlock. They may lead to deadlock. So as long as the state is safe, the operating system can avoid unsafe states, okay, and all deadlock can be avoided. If an unsafe state, the operating system cannot prevent processes from requesting resource in such a way that a deadlock will occur. So unsafe state means deadlock may occur in the system. So the behavior of process controls the unsafe states. Let us consider one example that we have 12 magnetic tape drive. This tape drive is nothing but a resource, and we have 3 processes P0, P1 and P2, and process P0 require 10 tape drive, means this is the need for process P0. P1 may require 4 tape drive, P2 may require 9 tape drive. So 10, 4 and 9 is a request of process P0, P1 and P2, and total available resources are 12. So suppose at time T0, the process P0 is holding 5 tape drive, process P1 is holding 2 tape drive and P2 is holding 2 tape drive, which is shown here. P0, here we have a maximum need 10, 4, 9, and currently they have 5, 2 and 2 allocated. Okay, so now once 5, 2, 2 means total out of 12, 9 are allocated, so remaining are 3. Now 3 resources are remaining. then how this will be result in safe sequence, that we will see. So at time t0 the system is in safe state. Right now this system is in safe state, and the sequence is same, p0, p1 and p2, 5, 2, 2. These resources will be allocated and system is in safe state. But suppose at time t0, okay, means this is the time t0, process p0, p1, p2 are in safe state with allocation of 5, 2, 2 resources to the process respectively. Okay, this is the safe state. Now at time t1, suppose process p1 request for 2 resources. Now 2 is less than these 3, okay, 3 are remaining resources, so it can be allocated to p1. Now the remaining will be 1, and now p1 finished its use, okay, and p1 releases all these 4 resources. Now the total remaining resources will become 1 plus 4, that is 5. Then next p0 request for its 5 resources. Yes, it can be granted because 5 are available. So p0 have given 5 resources. Now p0 completes its execution and it terminates, and it leaves all these 5 resources. So all these 5 resources will be released, and then total remaining resources are now 10. Then process p2 request for 7. Yes, obviously 7 is less than 10, so that 7 will be allocated to p2, and now remaining is 3. p2 will finish its execution and then it will terminate. So we can say that the process at time t1 is in safe sequence with the sequence p1, p0 and then p2. If this safe sequence is executed, then deadlock will not occur in the system. Okay, so this is what the deadlock avoidance algorithm for using safe state. Okay, these are the references. Thank you.